Hello, everyone, and welcome to our presentation in Deep Learning and Embedded Computer Vision for Terrain-Aware Autonomous Driving on Mars. Essentially, how can we increase autonomous planetary mobility, or how can we help the rovers up there to drive themselves? My name is David, and our team here at Harvard consists of Sean, Charles, Mohammed, and myself. Today, we'll be discussing our project and the progress we've made towards improving exploration efficiency and accuracy on Mars. Our presentation today will start with a summary of the project and key results. Then Sean will discuss some literature, followed by the methodology and results, which he will present alongside with Charles. Lastly, Mohammed will present the conclusion, and he can discuss some potential next steps for this project. Before we dive into the details, let's begin with a brief summary of our project and the key results we've achieved. Our project focused on implementing deep learning for image segmentation and embedded computer visions to improve Mars rover navigation. We did this utilizing the public AI for Mars dataset, which is around 300 to 350,000 images that Curiosity, Opportunity, and Spirit took while they were up on Mars. And these images have been overlaid by volunteers with identifications for what type of bedrock, rock, sand, soil, and such that they are, so that they can be used for training in our AI models. Using these, we have utilized advanced neural networks to analyze the images and identify things like obstacles and rocks and untraversable terrains, enabling for future rovers to plot an optimal course up there using AI. Successfully integrating robotic systems and using pruning techniques, we were able to reduce the computational resources required for real-time inference, making our solution more practical for deployment in remote environments like Mars or other planets, or even remote exploration, AI exploration here on Earth. Furthermore, we rigorously tested our models against various scenarios that we could determine in areas around desert and rock-like formations that we have here on Earth. And this is to ensure robustness and reliability. Our work lays the foundation for potential future improvements in the efficiency and accuracy of Mars exploration, with implications for both scientific research and potential future human missions to the Red Planet. Now I'll hand it over to Sean, who will discuss some of our literature review and methodologies that we used.
Hello, my name is Sean, and I'm going to be discussing a little bit of background on our project through a literature review and some previous work in the field up to a few weeks ago, in fact. So a little bit of background, just some basics of computer vision, which most of you have probably seen before, but what we are trying to do is on the very left, we're trying to work on semantic segmentation, which is essentially image classification at the pixel level. So we want to know every single pixel belongs to which class, right? We're not drawing a bounding box, right? Such as object detection around a dog. We want to actually determine which exact pixels belong to the dog, right? Whereas classification, right, and localization, that would be like, we want to identify this entire object is a cat, right? We're ignoring the fact that the cat is on grass and there's mountains in the background and the sky, right? Where semantic segmentation is really concerned with the entire image and what pixels belong to every class. So, one of the key areas of research that we looked into was actually a paper called S5, Mars Learning for Mars Segmentation. So they had broken apart the data set that we are using, the AI for Mars data set, into additional classes that were not part of the data set, such as the drilling holes and the trace from the rover and the actual rover itself. So we were able to leverage some modeling techniques from this paper, right? Such as using, kind of the standard UNet modeling, which is almost synonymous with image segmentation. But we took a more standard approach and used the the AI for Mars dataset a little more out of the box, and use the masks that were included with the dataset, rather than going down the additional class route that the S5 Mars project ended up going and using. So lastly, kind of in our literature review, and I would just be absolutely remiss if I did not include this in here. It is the segment anything model, right? This came out of Facebook just under a month ago, and it is absolutely fantastic, honestly. Just the level of capability for image segmentation has significantly moved forward in terms of state of the art. I mean, just looking at these pictures and the level of fidelity for segmentation is truly remarkable. So we didn't have time to actually try this, but it would have been pretty unique to send a few of those images through the segment anything, demo or code if available, and see how useful it could be. So secondly, I'm going to talk about the actual methodology and results for the image segmentation portion of our project. So the methodology for the machine learning portion here, at a very high level, right? I'm trying to keep this digestible, right, without getting into, what all the layers are doing in the UNet model, et cetera. But at a very high level, we have a data loader module, right, that is loading in our black and white images of Mars, right? We're only looking at one color dimension here, right? Just a black and white. The images that we have, contrary to the S5 data set that we looked at previously, which had color Mars images, the data set as it currently stands from the AI for Mars masked data only has black and white images. So we're taking those in combination with their masks, and those get sent through the UNet model, and then we actually get a color color by each individual pixel level predicted mask that is the output, and we'll get to those on the next slide as well. And then that gets sent back through, and we try to predict better masks, etc. But this is the general order, again at a very high level. So lastly, a little bit bigger results that we can actually see and digest a little bit here. And I think the legend kind of does a good job of kind of explaining what we're looking at here. But again, by the pixel level, we are looking at the majority of this is being classified as sand, which obviously makes sense, it being Mars. But we see the blue patches, at least on the left image, as soil, and that one is actually soil, which is pretty unique. But we actually see another soil patch on the left of that left-hand image, where which is actually classified red as big rock. So that one's actually an area of error that is just in this case unavoidable, because we just didn't have the necessary compute power. And then the image on the right is actually included for showing a bad example in this case, right? So we have soil being classified, or a rock being classified as soil, and we can see, you can see the underlying image actually, that's like a big chunk of hard rock. So that almost the bottom half of that right image should be classified as, either bedrock or red big rock. So interestingly though, right, because we wanted our model to run on an actual rover itself, we explored some pruning techniques. So the biggest one is really to just look at what weights we can remove from the convolution weights. And if we remove just 20% of them, we actually saw a 2x improvement in speed, which is pretty fascinating, especially if we want it to be on a rover, right? It might not necessarily matter on a Mars rover, right? Because they are relatively slow, so we could probably get away with like 1 frame a second or even slower if we needed to. But the fact that we can improve it through pruning techniques is actually pretty impressive. And what was really unique is that, using like an L1 drop off for pruning, right, which actually just removes the bottom 20% in our case of weights based off their L1 norm, we actually saw an improved intersection over union from 37 to 50, which is very, very impressive and a little bit surprising. So thank you. I'll pass it off to Charles.
I'll take a look at the robotic systems part of our project. So here the goal is to implement onboard inference on a Raspberry Pi using a camera module attached to it, and orchestrating the software using ROS, which stands for Robot Operating System, and then running the inference on the Google Coral. So what you see here is a diagram of our software, and you see on the left the Raspberry Pi and its camera module, and then in green you have all of the ROS components. And so in ROS, the way it works is you implement nodes. So your software systems are implemented as nodes, and they communicate with each other by sending messages to topics on a shared message bus. And so in this diagram here, you have the camera ROS node that is responsible for fetching images from the Raspberry Pi camera, where we used OpenCV to do that, and then publishing those images to the image topic. And then we have our inference node, which is responsible for consuming these images and then running them through our model to get the model output, which is a semantic mask, and then publishing those outputs to a predictions topic so that it can be consumed by other nodes downstream, though this is out of scope for this project. And then the inference node uses the Google Coral hardware to accelerate the model's output. So Google Coral is a accelerator hardware that we can connect to the Raspberry Pi that allows us to speed up model inference. And the reason being that deep learning models are quite computationally expensive, and they can take multiple seconds to actually output the prediction. And in a real-time application, a few seconds can be too slow, and so we wanted to run it on this accelerator hardware that can increase the speed by 100 times, if not more. And so in terms of result, we were able to successfully implement the camera and inference nodes in ROS, get the images from the Raspberry Pi module, and orchestrate everything in ROS, as I just mentioned. Where we run into a few issues is with regards to the shortages with the Google Coral USB. And so it has been out of order for months due to worldwide chip shortages. So what we did instead is we ordered the Google Coral M2 format of their accelerator, which essentially connects through an M2 port. Now the issue is that the Raspberry Pi only has USB ports. So what we try to do is order an M2 to USB converter, but then we run into firmware issues. There isn't a great way actually to convert M2 to USB. So that didn't end up working. So what we did instead was we reverted to running the model inference on the CPU, and we used ONNX to do that. So we compile and optimize the model through quantization, and then we use the ONNX runtime, to run the inference on the Raspberry Pi CPU. What that ended up doing is that the model took about 3 seconds to complete a single pass through the model, so to return the outputs. And in the context of our project, actually, since we're in the context of Mars rovers, they navigate quite slow, and so 3 seconds might actually be acceptable there for the rover to get the prediction from the model, and then change its navigation, right, depending on if a rock is detected or sand or any adverse terrain. In cases where the robot would move faster, 3 seconds is likely too slow, which is why we wanted to look at hardware acceleration. But yeah, so that's where we're landed. I'll pass it on to Mohammed now for the conclusion.
Greetings, and on to the conclusion of our project. This section includes concluding remarks and future work. So on to the conclusions drawn from this experiment, this project. We explored deep learning with pre-trained models for embedded computer vision using semantic segmentation. Multiple successful models were developed for Mars terrain classification in both TensorFlow and PyTorch libraries in Python. We successfully tested all models in cloud environment. From a hardware perspective, we explored hardware and software implementation aspects on a microcontroller, the microcontroller being a Raspberry Pi 3B+. with 32-bit initially and the 64-bit finally in terms of operating system. We explored temporal and spatial constraints and the limitations of real-time inference on hardware. We also explored various techniques to transform models from original state to lower complexity states. Okay, with that said, moving on to possible next steps or possible future work. So a comparison between base and lower complexity models would definitely be great to gauge the performance. Uh, it's generally considered lower accuracy, but accuracy levels, but a comparison would definitely be great. Explore various pre-trained model weights for terrain classification, preferably those trained on terrain imagery data. So a pre-trained model that specifically had this type of background and then was trained later on with our data set. We can explore additional sensors such as LiDAR or stereo cameras. We can explore and expand imagery data on other celestial objects, including moon and additional planets. We can explore future techniques to reduce model complexity. So some models that just are inherently complex architecturally may or may not work with complexity reduction techniques, for example, quantization. An example, we had a model that we tried among other models that had 50 that was spatially 54.8 megabytes in size, and after initial quantization, which was post-static training, post-training static quantization, reduced to about 30 or so megabytes. But this is something that most likely would need more exploration. So we can explore future techniques to reduce model complexity. That's what that was. We can explore hardware accelerators such as Google Coral Edge TPU. There were some limitations on availability this time around. We can investigate more robust evaluation criteria. We can also examine enhanced testing scenarios using real-time terrain simulations. It was one of the obstacles, in fact, that I had, where it just becomes prohibitive sometimes to actually have simulated terrain. So a simulated environment just has to be used to test the output. So that's what we have as next steps, and that's all for today. Thank you. Live long and prosper.